which is the introduction of Maria Galloway-Sprietsma. And I hope I did that right, Maria. And she was our guest speaker for this evening, and she will be speaking on pulsar timing. So Maria, take it away.
Hi, everyone. Thank you so much for having me. My name's Maria. I'm going to share my screen. I hope that's the best way to do things. I hope you can hear me all right as well.
Yeah, you sound good.
Okay.
And screen share is fine.
Okay. Just give me 1 second. Okay. So, oops, my thing is blocking some of the screen. Sorry, 1 second. Okay, there we go. So hi everyone, my name is Maria again, and today I'm going to be talking to you about timing with the stars or timing with pulsars. Oops, my mouse is not working. Okay, so a short introduction. My name is Maria. I go to the University of Arizona where I'm a senior. I study physics and astronomy there. And I've mainly been doing radio astronomy research the past 4 years. I have been studying the chemical composition of stellar gas clouds and molecular clouds. So I'm doing an ammonia survey on them for my senior thesis. I've also dabbled a little bit in astronomical instrumentation, still specifically with radio. And then for the past 2 summers, I was able to work at Rincon Research Corporation studying pulsars and pulsar timing arrays. I also just want to say thank you again for having me. I'm really excited to talk tonight. And I also received a Lucas Scholarship for the past year, so I wanted to say thank you for that too. So before I get into talking about pulsars, I want to talk about timekeeping. Timekeeping has kind of been this human endeavor that we've been on for a really, really long time. Timekeeping has been important for early humans to know the seasons for agricultural purposes. Knowing the time of day was really important when we started having more industrial revolution type jobs. And then ocean navigation uses timekeeping. It's a really important aspect of ocean navigation. And unfortunately, a lot of ship crashes have happened because of inaccurate clocks, especially in the 1800s when clocks weren't as accurate. Nowadays, very accurate timekeeping is really important in GPS navigation. So the satellites that are in GPS systems use very accurate atomic clocks. Physics and astronomy both utilize atomic clocks or other accurate clocks for things like particle accelerators. It's really important to have all of our telescopes in sync. So that's another place where very accurate timekeeping is really important. And then looking towards the future, space navigation, especially deep space navigation, is going to require really accurate clocks to keep track of our position. It's kind of like a mirror of ocean navigation. We needed pretty accurate clocks to navigate our oceans, and we'll need even better clocks to navigate space. So this plot here shows clock accuracy over time. I find it kind of interesting. Here we have the invention of the telescope, and then we can see kind of the clocks back then were not that good. So observations were kind of hard because we didn't exactly know what was happening at what time. And then in the 1950s, I hope you can see my mouse, by the way, but in the 1950s, we have the quartz crystal clock come around, and clock accuracy quickly improves until we get all the way to optical clocks. So I've been talking a lot about clocks, and I think a lot of people think when they think about timekeeping, they think about something with gears and numbers. But thinking more abstractly, a clock can be anything with regular periodicity. So this could be the rotation of the Earth, a swinging pendulum, and the way atomic clocks work is by having us measure their vibrational frequencies, which is another type of periodic oscillation. And if we think about this kind of interesting abstract version of a clock, which is anything with periodicity, we can kind of start to imagine even more things that could become clocks. Like, again, the rotation of the Earth, maybe the rotation of another planet, maybe something like a star. So anything with regular periodicity can really be a clock, even something like a pulsar. So I'm going to go over what pulsars are. That really nice video kind of went over everything, but I'm just going to go a little bit more in depth. And I'm glad it defined what a pulsar is, which is a rapidly rotating neutron star. So we'll start kind of with neutron star formation. How do neutron stars form? It's a pretty cool process all around, honestly. A star goes supernova once it reaches a certain age and starts producing heavier elements. And I'm sure most of you are familiar with supernova explosions. You know, the gas implodes, it's very, very powerful. And what's happening at the center of the star is the core is collapsing into something very, very dense, which is a neutron star. Neutron stars are incredibly tiny. Thinking back to that scale video we just watched, they're really, really small. They're smaller than our sun. They would fit over the city of Manhattan. They're some of the densest and smallest objects in our universe. They're densest, I guess. And yeah, so they're this ultra dense degenerate material. So here's a little animation of supernova happening over a long period of time. We see that huge explosion and the gas kind of coming off of the star. And then we can see here in the center a very, very small white dense object. And over time, that gas from that explosion fades away and we're left with a neutron star. And so here's an image, I believe this is taken probably in the X-ray, of a neutron star right here. They're very small, so they're kind of hard to see, or you're not really able to see them with the naked eye, but they're out there and they're very, very tiny. So getting into more how a pulsar forms from a neutron star, I have to talk about the classic physics experiment, the physicist in the spinning chair and conservation of momentum. So I'm sure we've all seen this where a physics teacher or someone is spinning in a chair and then they pull their arms in and begin to spin faster. So when we're talking about the creation of pulsars, we can kind of think of the neutron star doing just this. It is the core of the star that's becoming much more compacted and much more dense. And it's kind of like the physics teacher pulling his arms in here. And this density causes a much, much faster rotation. So the star is already rotating. And when the supernova happens and this neutron star forms, it begins to rotate incredibly rapidly. There's a lot of really, really strong forces happening and a really, really strong magnetic field forms. This magnetic field is really powerful in the context of stars, more powerful than maybe our sun's magnetic field. And these magnetic fields create these powerful beams of radiation that is like the classic pulsar image. So something that I like to remember is that not all neutron stars are pulsars, but all pulsars are neutron stars. So when we're talking about pulsars, we're talking about rapidly rotating neutron stars. So here's the classic image of a pulsar. We see those two magnetic field beams kind of shooting out, passing the field of view of the observer, and that would look like a blip or a detection on our telescope. And then here's a non-moving image with those radio waves that are blasting out of the pulsar. So pulsars were discovered in 1967 by Jocelyn Bell and Anthony Hewish. A fun fact is that they thought they were aliens because the signal that they detected was so novel and so periodic. The pulsar that they detected had a period of about 1.3 seconds, and it was right on time. And they were really, really shocked that something in space, something non-alien, was making such a periodic signal. Turns out it was not aliens; it was just a pulsar, and many more pulsars have been discovered since then. So this is one of the more famous pulsars within the Crab Nebula. We can see in this beautiful image the remnants of the supernova with the gas and the dust kind of going outwards. This top image, it's kind of hard to see, but it is an animation over 10 years, I think. And you can see that gas is kind of moving within the Crab Nebula. There's almost some kind of circular patterns here. And then this is an even more up close image. It's kind of hard to tell that anything's moving, but we see this neutron star here in the center with this ring of gaseous material around it. And then this right here, I believe, is a jet blasting outward from the pulsar because of those strong magnetic fields. A few other pictures of some famous pulsars. Here's the Vela Pulsar. You can kind of see that there's also a really strong jet shooting out from this one because of those really strong magnetic fields. And I think that this circular kind of image here is because of its rapid rotation, kind of mixing up that gas that is remnant from the supernova explosion. Here's an interesting system of two binary pulsars, which is kind of cool to think about the mechanics of that because they're both rotating so rapidly and then they're rotating around each other. So there's a lot of really strong forces happening there, really strong gravity. And then this is another image. It's actually a composite image. So right here is the neutron star. This is actually a magnetar, which I'll talk about in a little bit, surrounded by the supernova remnant. So there's been a lot of pulsars discovered since 1967. And what does the average pulsar look like? So the average pulsar has a period of 1 to 6 seconds. They can go, faster or slower than that. The slowest known pulsar, I think, is actually this one pictured here. I might be wrong on that, but this is definitely one of the slower ones at around 23 seconds, which is really slow. Average pulsars have really strong magnetic fields, and I say really strong in comparison to maybe like a normal star. There's a lot of stars out there, but I mean like our sun. And they emit really strong in the X-ray and gamma ray, and on Earth they're best observed at around 400 to 1,000 megahertz. But observations have been made in a wide variety of frequencies. So there are actually a few different types of pulsars. There's that typical pulsar that I talked about with a pretty strong magnetic field. They're mostly stable in their rotation. Then there's magnetars, which I mentioned, which by their name, you can guess they have extreme magnetic fields, 10 to the 15 Gauss. They emit really strongly in the X-ray, and they're really, really unstable because of their strong magnetic fields kind of warping their rotation. There's also some things called RATs, rotating radio transients, that are fairly newly discovered. I'm not really an expert on those, but apparently they're kind of a mystery because they turn on and off. So that's kind of a cool topic in pulsar science. And then finally, there's millisecond pulsars, which by their name, you can guess they have millisecond rotation periods. So they're rotating very, very quickly. And these millisecond pulsars are also very stable, and they have small magnetic fields. And their formation is interesting and a little bit different than that of a typical pulsar. So this is a pretty common plot in pulsar astronomy called the p dot diagram, where here the x-axis is the pulsation period, and then the y-axis is the spin down rate. So that can be kind of translated into the stability of the pulsar's rotation. And here we can see this large cluster of where the typical pulsar would lie, around 1 to 10 seconds of rotation speed. And then here, these blue dots are the magnetars that I mentioned. They're a bit slower, and you can see that they're also a bit less stable. And then if we come down here and kind of follow this line, there is another grouping of pulsars, which is where the millisecond pulsars reside. So they're very, very stable, very, very low spin down rates, and they're also rotating very rapidly compared to these average pulsars. So it's kind of like a whole other cluster and grouping of pulsars. So I'm going to walk you through the formation of a millisecond pulsar because it's a little bit different. They're also called respun pulsars, and you'll see why. So if we kind of follow this panel here, we can kind of ignore this for now, but this panel is really what I'm focusing on. So millisecond pulsars have to form in a binary system. We have a primary star and a secondary star in this system. Like I said, the primary star will go supernova and explode. Nothing really happens to this guy, he's fine. The binary star survives as a neutron star, and then we have this binary system that can probably exist relatively peacefully for a very long time. As this exists, this pulsar here begins to age, its magnetic field begins to decay, and it begins to slow down, and it's kind of like a dying pulsar. Eventually, the secondary star might start its own evolution. It might start to get older, and it will start expanding as old stars do. And when this happens, this material in the secondary star can start to creep over onto this pulsar. And our friend conservation of momentum comes in again, and this extra mass causes this pulsar to begin rotating very rapidly once again. And this can happen for a while, and we eventually achieve this low mass system with maybe a white dwarf or some other kind of small star, and this millisecond pulsar that has been respun because of the matter it accreted from its counterpart. And the important takeaway from this is that during the pulsar's lifetime, it kind of lost that really strong magnetic field, which is what causes a lot of instability in pulsars. So this pulsar hasn't fully lost its magnetic field. It's still quite strong, but it's lessened relatively to other pulsars. And this causes millisecond pulsars to be really, really stable. And they're also rotating very rapidly, as I mentioned. Oops. So this is a beautiful animation of what that might look like over time. We have our pulsar here that is a little bit slow. It begins accreting this matter, and it begins spinning faster and oftentimes begins emitting in the X-ray too, because it's spinning so quickly, getting so much energy. So like I mentioned, millisecond pulsars are very, very stable because they've had time for their magnetic field to decay. That p dot diagram I showed, if you remember, the spin down rate was really, really slow for millisecond pulsars. And this means that they rarely glitch, which is when the magnetic field kind of interrupts the rotation and causes some strange, unexpected pulsations. And because of this, because of their stability, they're actually some of the most stable objects in the universe. They're more stable than any other kind of pulsar, any kind of pulsating star, and any other rotating object. They're incredibly stable and incredibly long lasting. And so that makes them a really interesting object. And if we think back to the idea of clocks and what a clock can be, a millisecond pulsar could be a great potential clock because it is very, very stable and it has a periodic rotation. So we've studied about 2,000 pulsars in our galaxy, and around 300 of these are millisecond pulsars. They're not as many millisecond pulsars just because their formation is a little bit more complicated because they're in that binary system. And most of them are distributed around the galactic center. So this is a little plot I made in galactic coordinates of every known millisecond pulsar, and the darker color indicates a more rapid rotation. And you can see that most of them reside in the galactic center, which is expected because they need a binary counterpart to form. So now that I've walked you through kind of pulsar formation and millisecond pulsar formation, I'm going to talk a little bit about their use as clocks and their timing applications. First of all, why is this a useful field and why might we want to study this? So first of all, pulsar timing would be really great to independently check atomic clocks on Earth. We have a bunch of really accurate clocks, but we kind of check them with each other, which maybe could create some kind of error over the years if we're just checking these clocks like with one another. Probably one of the most lucrative things about pulsars is that they'll be continuous for billions of years, and they'll forever be in our sky pretty much. So that definitely beats atomic clocks in terms of longevity. And then also thinking more about GPS timing, we receive timing signals from our GPS satellites that are really, really useful in terms of communication. But pulsars can provide timing data independent from those GPS systems. So that's really useful if we think about, oh, what if we don't have GPS satellites to provide our timing data? Pulsars can provide that potentially. So some current applications that you might be familiar with in terms of pulsar timing, the biggest one is probably nanograv. Nanograv is attempting to detect gravitational waves using pulsar timing. They use a pulsar timing array. So I think I'm most familiar with gravitational waves detected via LIGO. This plot shows what kind of gravitational waves you could detect based on your detection method. So these ground-based interferometers is what LIGO used. LIGO detected the neutron star merger, black hole merger. These are higher frequency gravitational waves. Nanograv, using the pulsar timing array, would be able to detect a lower frequency gravitational wave. So something from a supermassive black hole, or possibly even primordial gravitational waves, which could tell us about the early universe. So this is a really, really interesting field that is utilizing pulsar timing. Another application that is kind of up and coming is XNav, or X-ray navigation, or X-ray pulsar navigation. And this would be really useful for deep space missions that are traveling possibly beyond our solar system, within our galaxy, and don't necessarily want to communicate with Earth or can't communicate with Earth. Pulsar timing for deep space missions will definitely be important, because pulsars can kind of provide a cosmic map of where you are, and you don't have to communicate with Earth to figure out your location. So if we're going really, really into deep space, this would be really useful. NASA actually recently demonstrated that this would be possible with equipment attached to the ISS. They observed 52 X-ray pulsars, and were able to show that X-ray pulsar navigation is possible. So pulsar timing and navigation is really what I'm talking about. Just a general overview. Pulsar timing works by receiving the pulsars emitted from these millisecond pulsars, which act as very stable oscillations, which, as I talked about, can potentially act as a clock. Telescopes can receive these signals and construct timing data. And then in space, we can use these pulsars kind of in the way we use GPS satellites. So this is the gold plate from the Voyager mission. This is, kind of that iconic image. This is actually a map of Earth based on the pulsars that are closest to us. So pulsar timing is really up and coming and really, really interesting. And the question that I was kind of tasked with answering was, can timing signals from pulsars be used on Earth for ground-based GPS applications? So not in space, just normal GPS on Earth. So I'm going to go a little bit in depth on the research that I did for the past 2 summers on pulsars and GPS. First, I'm just going to do a quick GPS overview. We're probably mostly familiar with how it works, but it's good to be on the same page. So GPS has 3 components: the satellite segment, or satellite constellation, which is 24 satellites that surround Earth. These satellites are all equipped with atomic clocks that transmit timing data. There's also the control segment, which is these larger telescopes or antennas that are receiving this timing data. And the control segment helps monitor and keep track of the satellites so that they don't get off track, and so that their atomic clocks stay synchronized. And then there's the user segment, which is you and me and our cell phones, and the military, which is probably like the biggest user of GPS. And we are receiving these timing signals from these satellites that allow us to calculate our position. So a little bit of a simplified version on how this works. If we imagine we are somewhere on Earth and there are a bunch of satellites above us, these satellites are emitting timing signals in a spherical fashion. It's a light signal, so it goes out spherically. And we are able to receive that signal from one satellite, and then another satellite we could get a signal from, and then a third satellite, and sometimes even a fourth one. And we kind of triangulate our position based on these signals that we are receiving. And because these are timing signals, we can convert those into positional data. So this is kind of a simplified version of how GPS works. So now thinking about where pulsars could come in to GPS timing, this is a schematic that I made. It's kind of rough. But the question I was thinking about is this kind of design. So what if there were no GPS satellites? Could we use pulsar timing data to replace the atomic clock timing data that these satellites are emitting? This is kind of my rough sketch of what it would look like. This project was largely a feasibility concept project. So these are the pulsars that we would be hearing from. We would hear their timing signals. They would come down to these ground stations that would detect the signals and then transmit this data to the user. So there's definitely a similarity between, these satellites with their own timing signals and these pulsars with their timing signals. So before we start knocking out our satellites and replacing them with pulsars, we need to ask a few questions. First of all, how stable are these pulsars? How stable are they as clocks? Because atomic clocks are very, very accurate. And the timing data that we need to calculate a very, very accurate position needs to be very precise. A small timing error can produce a large error in positional data. Secondly, we need to figure out how to convert the pulsations into a timing signal. So that was one of the questions that went into this research. And then we also need to figure out how we can observe these pulsars from Earth. What's the best way to do that? So first, I'm going to talk a little bit about stability measurements of clocks and pulsars. Clock stability is generally measured using Allen variance, which is kind of like a sigma least squares method type thing. It's complicated. I'm not going to get into it, and I'm also not an expert on it. But that's what is used to compare different types of atomic clocks. Pulsars aren't really able to use this Allen variance, Allen deviation calculation because they are pulsars and they have different frequency drifts and different pulsation methods, and it's just very different from the terrestrial-based clocks we have. So there's the sigma z method that is used, and sigma z allows the stability of a pulsar to be directly compared with the stability of a ground-based atomic clock. So here's one of these plots that was made using Allen variance and sigma z. This y-axis here represents the clock stability, and the lower or more negative this number is, the better stability. And then this time scale is kind of how long we've been, honestly, it's how long we've been getting to know the timing signature. How stable is it? What is it doing? The longer we observe something that's pulsating, the more we know about what it's going to do. So the time scale, that's kind of what that means. And we can see here, there's an atomic clock that goes pretty straight across and doesn't really change in terms of stability. And then there are 3 pulsars. These 2 pulsars kind of go up and down in terms of their stability. And then this one, you can see, surpasses the atomic clock and becomes much more stable than the atomic clock after a little while. So this is really interesting, that pulsars can potentially be better clocks than atomic clocks. Here is another plot with more frequency stability measurements, and this includes many more clocks. There's the hydrogen maser. Here is the cesium atomic clock, which is probably one of the most common atomic clocks, and I think that this is the one on board the GPS satellites. And then here's a rubidium atomic clock, and you can see that the stability goes down over time, certainly, and then it kind of evens out and maybe goes up a little bit. I'm not really sure why that happens, to be honest. But then here is a pulsar, and we can see that over time, as we observe this pulsar for longer and longer, the stability goes down and it eventually begins beating the rubidium clock and then beating the cesium clock. So this is really, really interesting, that a single pulsar could potentially, after a while, become more stable than our atomic clocks that are on our GPS satellites. And again, we want more stability in a clock because that means we have more accurate timing signals, which means we have more accurate positional measurements. So the previous plots I showed demonstrate that pulsars can begin to become competitive timekeepers. It does take a while of observing the pulsars and getting to know their timing signals, but after a while, pulsars could potentially be better than atomic clocks. I would also keep in mind that all of the plots I showed are just for the observation of a single pulsar. So if we potentially had a system where many pulsars were being observed kind of in an array, the stability of the system could go down even faster. So there's a lot of potential to be explored here in terms of how stable pulsars are. So next, in terms of my research that I did, one of the biggest things was figuring out the positional calculation technicalities, and then how would we observe these pulsars for initial testing and future use. So a few slides back, I showed that plot of those satellites with the spherical signals being emitted, and that is essentially how GPS works, kind of via triangulation. So that's called time of arrival. You're measuring the time of arrival, the signal that comes to you. And in terms of pulsar astronomy, we can get a sigma or a positional error based on the width of the pulsar and then the signal to noise of our measurement. So this is the equation used for time of arrival. Oops, my mouse went away. For time of arrival. And then over here, another method is called time difference of arrival, which is to me a little bit more confusing. It kind of utilizes these parabola type shapes and intersects them to find the user position. And this is a difference of time. So this method requires at least 2 receivers or anchors to difference the time measurements. And this equation here is kind of what goes into calculating the positional error from a time difference of arrival calculation. It takes into account the bandwidth of your antennas, your integration time, and then again, your signal to noise. So a large part of my research was comparing these two. So calculating the sigma or the positional error from TDOA, I found gave much, much better measurements. So this is interesting because our GPS systems use TOA, but I found for pulsar applications, TDOA would provide a much, much better positional measurement. So the range error, so this number is the error that I get in position, hypothetically, using these parameters. Hypothetically, with pulsar observations, we could get a positional measurement of 0.52 meters, which is pretty good. I mean, modern GPS is a lot better, but for kind of this rough sketch, I was really pleasantly surprised that pulsars could hypothetically give us a positional error of just half a meter. I found using TOA measurements that the error would be around 500 meters. So definitely not as good. There's definitely a trade-off between the two. TOA is a lot simpler. So maybe if we were in space, you know, deep space, 525 meters wouldn't be that big of a deal. But for Earth-based navigation, we really want that precision. So then finally, we needed to figure out what kind of observations we wanted to do in the future and what kind of telescope we would need in the future if we wanted to do these experiments. Some of the basic parameters that we decided on were a signal to noise ratio of 10. So that's kind of what we were aiming for in terms of quality of the observation. We wanted low integration times, so we didn't want to have to point our telescope for that long at the pulsar. Small dish size, and ground-based observations. I guess these are all kind of things that anyone would want in an observation, you know, small dish size, low integration time, but this is what we were striving for, because if we're thinking long-term, implementing these pulsars into a GPS system, you know, we wouldn't want everyone having to lug around a giant telescope. So first, we needed to figure out what frequency would be best for Earth-based observation. You can see this plot here demonstrates the flux density of pulsars over frequency. So as we go to higher frequencies, the pulsars get dimmer and dimmer. So these plots kind of indicate that we want to aim for lower frequency, or around 400 to 1,000 megahertz, because we want a larger flux density, which is basically just brighter. That would be better. So a useful plot for every astronomer is this one that shows where we can observe and where we can't. After doing research on where pulsars are the brightest, I kind of figured that observing around 75 centimeters would provide the brightest pulsars, but also the most studied pulsars. So at 75 centimeters is where most of the pulsar research goes on, which is right, oops, I lost my mouse, right around here. Unfortunately, this right here, it would be nice to observe pulsars more in this range, but we kind of get knocked out there by the atmosphere and stuff. So 75 centimeters was the goal. So here's just a comparison of flux density between 400 megahertz and 1400 megahertz of these pulsars. The size of the circle actually represents how bright the pulsars are at these respective frequencies. So you can see this plot has larger circles. This one's very bright. A lot of bright ones right here as well. And this one, they are not very bright at 1400 megahertz. Maybe this one, I think this is the Vela Pulsar. So that's kind of unfortunate because it's easier to observe at 1400 megahertz with the equipment that was potentially available. But 400 megahertz was much brighter. So something else that kind of went into this research was what size telescope would we want to use for this hypothetical GPS system. So if I want a really good signal to noise, the best thing would be a very large telescope or an array of telescopes that were very large. But we wanted to aim for something small and cost effective for possible future implementation. So I decided that an interferometer or an array of telescopes would be the best option for this. There was a lot of in-depth work that went into calculating the size of the telescope, and I actually worked on this over the next summer as well. But this is the main equation that kind of went into that thought. This takes into account the signal to noise, the width of the pulsar, and the pulsation period. Integration time comes in, it's pretty important. And then the sky temperature and the receiver temperature as well are pretty important. So there's a lot of factors that go into calculating the telescope size. On top of that also, cost, thinking about cost effectiveness. These are some plots that are a little bit boring, but this is just a dish size visualization at 400 megahertz compared to 1400 megahertz. If you look at this y-axis here, you can see that the dish radius for 400 megahertz is much smaller over here. And if we jump onto the plot on the right, the dish radius would have to be much, much bigger to achieve the integration time we wanted. And this is also an idealized calculation. So things got a bit more complicated than this. So a large part of my research was kind of figuring out the ideal pulsar observing telescope. And so part of that was using existing telescopes that were available to figure out how long we would need to observe. So if we had 4 6.1 meter dishes, that would be a 16-second integration time, pretty good. I also considered long wavelength array antennas, using 5 of them in an array, which would give around 300 seconds. Same with 2 5-meter dishes, around 300 seconds. 8 1.8 meters, we go around 13 minutes. And then after that, it starts to get worse and worse. So there's kind of a conundrum here. Trying to figure out what is the most cost-effective telescope to use, what will give us the signal to noise we want, what will give us the integration time we want. There's a lot of thought that goes into that. I eventually decided on some kind of interferometer, again, using these equations. Here's just some numbers that I crunched out for observation time, and it really varies drastically based on the number of telescopes or antennas in your array. So we could go anywhere from 8 days to 12 minutes, depending on the diameter, and then this one is only 3 days to 4 minutes with 5 telescopes. So this experiment is obviously there's a long way to go with GPS-based pulsar timing. And the current infrastructure that is available to test these pulsars out and do actual observations is really plentiful. There's a long wavelength array, which I mentioned, the very large array. A lot of telescopes in Australia have already done pulsar observations and would be especially suited to this. And I've listed here mostly large arrays of telescopes, but I think that something really interesting that can be explored with this kind of timing array is more citizen science and using a larger set of smaller antennas that are a lot cheaper. So a large number of cheaper antennas I think would be something interesting to try out going forward in this experiment and thought process of trying to observe these pulsars and measure their time difference of arrival for eventual GPS applications. I also wanted to mention this really cool software that I was able to use while doing this research, which is called Project Clea. It's free. online if you look it up. If anyone is interested in pulsar astronomy, I was very surprised by how cool it was and how many things you could do on it. So this is not this isn't like a paid advertisement or anything. I just thought this was interesting. You can input your telescope parameters, so you can choose your diameter and what frequency you want to observe at, and the gain, the bandwidth, things like that. And then you can also put in your location. And this software has a catalog of pulsars to choose from, and you can try and observe one. So that's kind of cool. And it gives you this fake little pulsar data. This is one that I observed at 400 megahertz. So this is kind of an interesting way to get more involved in pulsar astronomy. So some conclusions about the research I did and also about pulsar timing in general. I think that pulsar timing is going to play a huge role in deep space navigation. I think that deep space navigation is actually going to have to rely on this pulsar timing, on these pulsar timing signals to go deeper and deeper in space. If we ever get there, if we ever even get to outer galactic travel, we're going to probably lose touch with Earth a little bit, and pulsars can provide kind of their own GPS satellite configuration for us to explore space with. I do also think, based on my research, that pulsars have the potential for Earth-based navigation. And I think that they could be implemented in a GPS type system, but there's a lot of work that would need to be done in terms of infrastructure, observations, and then probably the most complicated part of GPS timing with pulsars is getting that pulsar data to the user. Because right now our phones can, intercept that GPS data, but it's a lot harder for our phones to intercept data from pulsars. I also think that pulsar timing would be a very valuable backup system to GPS satellites. So if we started, a pulsar timing array now, and one day our GPS satellites went out, we could have a pulsar timing array for a backup that would keep our communication systems live. And then I also think that in general, their long-term stability could be used to stabilize terrestrial atomic clocks, which would be something really interesting. The best part about this field is that the longer you observe the pulsars, the more stable that they get, because we learn more about them. So there's only upward from here in terms of pulsar timing and pulsar astronomy. So I just wanted to say thank you to the San Diego Astronomy Association, the Lucas Scholarship Committee, and then I did this work at Rincon Research Corporation. So thank you to them and my advisor, Dr. Katie Keating, who helped a lot with this work. And if there's any questions, I would be happy to take them.
Yeah, Maria, if you'll open your chat window.
Oh, yeah, okay.
There were several questions that were posed.
Okay, I'm sorry I didn't see them.
No, it's all right. Some speakers don't like being interrupted anyways. So if you would, if you can find those, I saw at least two go by. I might missed more.
Yeah, I see the first one. Jocelyn Bell is my aunt. I saw your last name and was thinking that. Okay, sorry, I'm reading through them. Is the pulsar period from spin of the star or precession? So the period is from the precession of the, so that's actually a good question, but yeah, I believe it's from the precession of the, from the magnetic field radiation beam crossing our path. That's where the period comes from. Sorry, that was kind of a short answer. I hope that did that. Yeah, so why does the pulsar beam vary or move from the spin axis of the original star and the pulsar spin axis? This is a really good question. I actually wonder this myself, and I'm not entirely sure, but I think it's kind of, I think it's just kind of arbitrary and random, and it depends on the mechanics of what the neutron star is doing when that supernova goes off and when it initially starts spinning really quickly. So I think that's kind of a complicated answer that just has to do with the initial mechanics. I do not know Vanessa, but I could get in contact with her, Steward.
And also I have a reminder from the Wizard of Oz, who's running from behind here. If anyone wishes to ask a question of Maria, please unmute yourself and we can ask her verbally. So we try to mute everybody while you talk, Maria, so that you're not interrupted. But
Okay, yeah, so I see, can pulsar period variations detect gravitational waves? So yes, that is kind of, well, that's a few slides back, but that is kind of what nanograv is doing. But the gravitational waves that nanograv is attempting to detect with pulsar period variations are really, really low lying and low frequency. I'm not an expert on this area, but they're really, really low frequency. And so you have to observe the pulsar for a very long time and continually observe multiple pulsars to make sure the period variation is actually from a gravitational wave. And so nanograv actually, I think they just released their 12.5-year data set or their 15-year data set. So it's been a long time going that they've been collecting this data and looking for very, very minuscule residuals in pulsar timing data. But yes, that could potentially detect gravitational waves. How does a pulsar differ from a quasar? I'm embarrassed that I don't immediately know. I think quasars are not necessarily from neutron stars. I think a quasar could also be from a black hole that is causing matter to shoot out as well, but it does look similar to those images that I showed with those pulsars, with those magnetic beams. Or I'm sorry, the jets of gas and dust. I think that a neutron star can cause that as well as a black hole. So a quasar maybe could be caused by a pulsar, but also a black hole.
Other questions? Well, I have a question then. Has pulsar timing, was that used when they made the picture of the supermassive black hole in M87? Because they had a bunch of global radio telescopes that all need to be synchronized.
Yeah, they did. So I don't think they used, to my knowledge, I don't think they used pulsar timing, but they did use very, very accurate atomic clocks to synchronize their telescopes at the very least. So that's as far as I know about that. But pulsar timing would be a great application for that, in my opinion.
Okay. I have a question. In the 400 megahertz band, can you sort pulsars by frequency, or are these wideband signals and you're looking at multiple ones and you're essentially sorting by direction of arrival, or did you use frequency selectivity? Now, are they at different frequencies?
Yeah, so that's a great question. I didn't get that far, but I believe pulsars, that it would be a wideband signal, and you would have to, tune up to the pulsar. And then 400 megahertz is kind of a complicated frequency range to observe in because there's a lot going on. So that is a question that would also need to be answered in terms of this research for like GPS applications. Can you see the neutron star at the center of the Crowd Nebula? Yeah, so the image I showed, I believe, was taken in the X-ray. And you can, I mean, there is a spherical ball there, but I think that's mostly gas, and the neutron star is somewhere in the center of that. That would be my answer.
Next question for Maria.
Maria, I have a question.
Yeah.
I'm not sure I fully understand the quasar or the pulsar GPS concept. You've got several telescopes, and each one of them is acting as a relay, basically, of the pulse train to the user.
Mm-hmm.
So each telescope is observing. If it's TDOA, then each telescope is observing just a single pulsar.
Yeah.
And the time delay to the user is what allows them to geolocate themselves.
Mm-hmm.
But what about the atmosphere? Doesn't the fact that you're transmitting through different pretty much horizontal atmospheric paths kind of mess up the TDOA, or does it have an effect?
Yeah, it definitely could. So the whole issue of taking the pulsar timing data and then transmitting that to the user is we didn't really get that far yet, so I haven't gone super in depth into that. But I do think the atmosphere could cause some issues there. I guess if you're doing TDOA and transmitting, yeah, there's a lot of complicated issues in terms of that specific aspect of the timing for GPS applications.
Yeah. Okay.
That's a great
now
point.
I think I understand the concept a little better anyway. Thank you.
And Maria, I think you got another question in the chat.
Yes. Is light directly? Oh, so that's a great question. It probably depends a little bit maybe on what frequency we're observing at, but the light, well, yes, this could get complicated in terms of timing as well. The light should be directly from the neutron star because that would be the most stable pulsation. I think that there are probably indirect effects from the radio and magnetic waves sweeping through space and the gas that cause timing delays and timing errors, but the light is from the neutron star. Oh, and then are there specific pulsars in general that someone, yeah, so the question was, are there specific pulsars in general that someone like NASA would consider for GPS application, like ones that are always in the sky? Yes, so pulsars, there's a good geometric distribution of pulsars actually, which is why I had those plots of all the pulsars with galactic latitude and longitude. So when choosing pulsars for a GPS application, you'd want pulsars that were continuously up and pulsars that were the fastest and the most stable ones. And then another thing to consider when choosing the pulsars, would also, sorry, I already said that, but would also be when they're up. So a part of my research was actually just figuring out what pulsars are in the sky, specifically in Tucson, during what times of the year. So that kind of turns into a complicated mathematical issue of, oh, this pulsar is here, now it's not here during this time of the year. So that's another issue that goes into GPS pulsar timing.
Another question? And you can unmute yourself to ask Maria a question. No? All right. Well, I have another question. Maria, can you talk about what the next step in your research would be?
Yeah, absolutely. So the next step is actually just observing pulsars and trying to get that TDOA figured out and figured down what we would do. So that's why at the end of my talk, I kind of was talking about what infrastructure is currently available to observe the pulsars. And then I also had that plot about what the integration time would be and whatnot. So the next step would certainly be to get an observation plan, find specific pulsars to observe, and then conduct TDOA measurements.
Maria, we had one person ask, what is the closest pulsar to our solar system and where is it located in the celestial sky? Oh
gosh, that's a great question. I actually don't know. There's so many pulsars. If I go back well, that's going to take a while. If I go back, maybe if we look here. This is kind of confusing because it's in galactic coordinates, to be honest. I honestly don't know. That's a great question. Maybe we'll do some research after this.
I have another comment. Dave, as long as you're there, would you like to say a few words, Dave, about the Lucas scholarships that Maria mentioned at the beginning of her presentation? Because many of our members probably don't even know about this.
Well, I could say something, but I don't know as much as I should. We had an endowment fund set up as the Lucas scholarships. Maria, you're at the University of Arizona, is that correct?
I am, yeah.
Yeah, see, that's one we didn't even know about. Our Lucas Scholarship Fund, the one that I'm more directly involved with, is actually set up at San Diego State University. But obviously, we've got something that I wasn't aware of going on at University of Arizona. It's done very well. This year, at least at San Diego State, they've opened it up to significantly more students. So because the investment of the endowment has done very well, those grant funds have been opened up to quite a bit more students. I believe we had 15 students this year, at least at San Diego State University, that benefited from the scholarship. So, and I wish I could speak more about the one at Arizona because that completely caught me off guard until our last board meeting.
So just to kind of recap that whole thing, the San Diego Astronomy Association, through a generous gift of one of its members, has an endowment that provides scholarship money to future astronomers. And we're very glad to help the astronomy community by giving back in that way. So, all right, did I see another question, I think, or was that a comment go by? Question for Maria?
There is a chat window here that says from a quick Google search, PSR J0108-1431 is the closest known pulsar to Earth. And it's about
I'm sure that's what Maria would have said.
Of course, absolutely.
Right, Maria?
Oh yes, that's was on the tip of my tongue.
Right on the tip of your tongue, you know. Okay. Last question for Maria. Does anyone want to take the last question? Nope, I think we're all...
Wait, I have one.
Oh, go ahead.
What do your parents think about your research and your major?
They're very proud of me and very surprised that I'm studying physics and astronomy. They didn't expect that, so yeah.
Well, I can say on behalf of the San Diego Astronomy Association and our guests from Michigan that we're also very proud of you. And I want to thank you for your talk, and maybe a little applause if people want to unmute and give Maria a little round of applause, and thanks for her great talk. So with that,
thank you so much.
That is the end of our meeting for January.